Welcome to the final session on deep learning. I'm Philip Cranbull. Philip Isola and I are going to chair this session. And just like any other session, we'll have 3 orals followed by a 3-minute question period. There is 3 microphones in the room. There's one here on the side, and then there's one on each level. So please, during the last talk, towards the end of the last talk, line up behind the microphones and ask your questions. They're going to be much more interesting than whatever Philip and I come up with. So please come up, ask questions after the talk. And I guess the one other thing is, please do not walk out after the last talk. Wait until the last question session is over to walk out. Philip and I will see you and we'll know who you are. All right. Good. With that, let's get started.
Hello, everybody. If you take out your phone right now and shoot a picture, you'd probably be using a lossy image compression algorithm. The output of the sensor is going through an encoder which saves it as a bit stream, and when you look at the image later, you look at a slightly degraded version of what you took a picture of. However, maybe you don't want that. Maybe you're a professional photographer or you're working with medical images. In such applications, we really must preserve our images. That's where lossless image compression comes in. Here, the output of your decoder is exactly the image you put in. In this talk, I'll present our work, which is the first practical learned lossless image compression algorithm, and it produces small bit streams fast. To explain how, let's start with general lossless compression. Here, you have some symbols distributed according to a probability distribution P. Now, you get a message. This is just a stream of symbols, independent and identically distributed. You want to encode them into a bit stream such that when you decode later, you get the symbols back. For this, there are various algorithms out there called entropy coding algorithms. Examples that you might know are Huffman coding or arithmetic coding. These work by outputting bits depending on the probability distribution of a symbol. More likely symbols get fewer bits. So we need to know P or an estimate of it. The problem for us is that P of natural images is unknown. So we aim to learn a probabilistic model P tilde. We aim to minimize the negative log likelihood of P tilde, which is the same as minimizing the bit cost of using P tilde to compress symbols that are actually distributed according to P. Note that no matter how bad this P tilde is, you can always do lossless compression. You might just use a lot of bits. So how do we learn this P tilde? First of all, we'll use the pixels of an image as our symbol stream. In contrast to the default lossless compression case, these are not independent at all. They're highly correlated. So we want to somehow learn the joint probability distribution over all pixels of an image, P tilde of x1 to xn. We must factorize this joint somehow. Otherwise, learning is intractable and entropy coding is impossible. One option for the factorization would be a causal factorization over pixels. Here, P tilde of xi depends on all pixels to the left and above. We want something that produces P tilde. I'll visualize this here with a black box. How do we use this black box for entropy coding? P tilde now changes for every symbol in the stream. That's why we use adaptive arithmetic coding. That's an entropy coding algorithm where the probability distribution can change while encoding. You just need to make sure you also know it while decoding. So, to compress an image, you would go over it pixel by pixel. In every step, you would feed all previous pixels to the black box. You get P tilde, you feed that to an adaptive arithmetic encoder, which updates the bit stream. Later on, you can decode. Again, you use the black box, but now you feed already decoded pixels to it. This way, you obtain pixel by pixel from the black box. Now, if you're familiar with autoregressive generative models, you might notice that PixelCNN uses this causal factorization. It turns out image generation literature studies a very similar problem as lossless image compression. They also learn a model P tilde, and they also aim to minimize negative log likelihood. They just use P tilde for sampling. So, are we done? Can we just use PixelCNN for lossless image compression? We could, but it would be slow, as these approaches require 1 forward pass per pixel. That's where our approach comes in. Instead of factorizing over thousands of pixels, we factorize over a few learned auxiliary variables. We start by extracting a learned lower dimensional representation from X, which we call Z1. Then we condition on Z1. When decoding, we can now predict P tilde in parallel for all pixels. But wait, now we need to know Z1 for decoding. To get this, we save it with adaptive arithmetic coding by learning a p tilde for set 1. We condition this p tilde on another, even lower dimensional representation. We do this recursively until we end up at a representation so small that we can just save it directly without learning a p tilde for it. So here I'm showing runtime comparisons to multi-scale pixel CNN, the fastest pixel CNN-based approach, and we can see that we obtain massive speedups of more than 3 orders of magnitude. Furthermore, even though this is the first practical learned lossless image compression algorithm, we already outperform the major non-learned ones, PNG, JPEG 2000, and WebP. I want to emphasize that the beauty of learning algorithms is that you can adapt to a domain such as medical images, and we believe that much exciting results are ahead of us. That's why we released all of our code and pre-trained models. Thanks for your attention. See you at our poster number 1.
Hi everyone, I'll present my paper titled as Image-to-Image Translation via group-wise Whitening and Coloring Transformation. I'm Wonwoong Choo, and these are the co-authors of my paper. First, I'll describe a task that we perform. The task is a paired image translation that aims to translate a given image to the target domain without the paired dataset. We also perform the exemplar-based image translation that aims to translate a given image to the target domain based on an exemplar. In this paper, we focused on how to combine the given content and the style. As a baseline, Munit exploits ADIN when injecting style to the content. It plays a role of matching the channel-wise mean and variance of the content feature to those of the style feature. From this perspective, what if the covariance among different channels is also included in the matching statistics? We assume that the style information may be reflected more deeply as shown in the comparisons. In response, we aim to match the interchannel covariance in addition to the channel-wise mean and the variance. I'll briefly describe the original covariance matching process. First, it performs the whitening transformation that makes its covariance matrix an identity matrix. Next, it obtains the coloring matrix and multiplies it with the whitened feature so that the covariance of the output feature is the same as that of the style feature. However, whitening and coloring transformation, in short, WCT, is computationally intensive and its backpropagation is non-trivial. In response, we directly approximate the output of WCT with novel regularization methods. So the content encoder naturally encodes the content feature whose covariance matrix is an identity matrix, and the style encoder encodes the coloring matrix. We further proposed to expand our method in a group-wise manner for the sake of the memory and time efficiency. Hence, the content encoder naturally encodes the feature whose covariance matrix is the block diagonal matrix, and each block is the identity matrix. Similarly, the style encoder directly encodes the coloring matrix represented as a block diagonal matrix. We perform user study in order to compare the output based on the human perception. The left figure shows the sample of our user study. A given question is which one best reflects the style of the exemplar while maintaining the identity of the content. And each user evaluated 60 sets of image comparisons. The results illustrated in the rightmost column of the table shows the superior performance of our proposed method in the most translation cases. Next, we evaluate classification accuracy for measuring the overall translated quality. To this end, we exploit a pre-trained classifier and fine-tune it on syllabi dataset. We check whether the generated image is correctly classified into the target domain. The results shown in the table demonstrate the superior performance of our method in the most cases. We also applied our method to artworks dataset. Rows indicate the dataset and columns represent the models. The results verify that our method shows the stronger style reflection than Munit. For example, the river color of ours in the blue rectangle is black extracted from the exemplar, while the color of the river remains unchanged in case of Munit. Similarly, our result in the first row illustrates better the artistic style of the exemplar compared to other baselines. This figure shows the comparisons on syllabi dataset. Translation cases are described in the caption. Our result in the third row of the right macro column shows more natural with more hairs than baselines. Furthermore, our result of the second row of the left macro column shows the bigger and more natural smile than other baselines. These results verify the superior performance of our method. We visualize the effects of our proposed whitening process in the third column of the left figure. It demonstrates that the group-wise deep whitening transformation makes the content feature lose the style, including color, but maintain the underlying structure of the content image. Finally, the right figure performed in various data sets verifies the robustness of our proposed method. Thank you for listening, and details will be provided in the poster session number two. Yeah, thank you.
Hello, I'm Yuan-Ting from the University of Illinois, Urbana-Champaign. I'll discuss the max slice Wasserstein distance and its use for GANs. In this work, we first analyzed limitations of current GAN training methods with a focus on sample complexity. We introduced the max slice Wasserstein distance as an alternative. Finally, we demonstrate its benefits theoretically and through experiments. Many of you have trained GANs. For early variants, you may see results similar to this. Depending on the initialization, training sometimes succeeds and sometimes fails. How do we address this? Numerous solutions have been proposed which fall into roughly two categories. First, improving the network architecture. Examples are DC GAN and progressive growing. Second, improving optimization dynamics. Examples are the Wasserstein GAN and the update rule by Hoyster and others. Our method is related to the second direction, so let's take a closer look at it. Among the first to study the training objective is the work by Agustsson and others, who identified the limitation of the original Jensen-Tschannen divergence. They proposed the Wasserstein distance. However, the Wasserstein distance in a high-dimensional space is estimated via a discriminator. This introduces the instability of training, which was addressed by the sliced Wasserstein distance. The sliced approach computes the Wasserstein distance by averaging. We project samples into many one-dimensional spaces. Computation of the Wasserstein distance in 1D is easy. Moreover, two high-dimensional distributions are identical if all 1D projections match. This gives rise to the objective on the slide. To illustrate this objective, consider samples drawn from two distributions shown in red and blue. When projecting the data onto the black line, we obtain the marginal distributions shown on the right. Given this histogram, it isn't hard to compute the Wasserstein distance for the projection direction. This significantly improves the stability of training since it reduces the dependence on a discriminator. Indeed, the vanilla sliced Wasserstein GAN has no discriminator. But what's the catch? Let's consider how many random Gaussian directions we need in order to tell apart two images. For the example on the slide, the two images are completely different. Notice the pixels at the corners. Projecting these images with a random direction means element-wise multiplication of each pixel with the number drawn from a normal distribution. With a sufficient number of pixels, both images project to the same value. For the contrived example, we receive very little training signal, and we need a lot of random projections in order to tell them apart. How to fix this? In order to fix this, we propose the max slice Wasserstein distance. Instead of averaging randomly chosen projection direction, we use a single yet informative direction, which is the max direction. Since we use the most informative direction, it converges much faster in the number of iterations. We provide a detailed analysis showing the theoretical benefits of the proposed approach. Now, how well does this work in practice? When learning the mean of a Gaussian in 10, 100, and 1,000 dimensional spaces, we compare the distance of the true mean to the learned mean over iterations. We show this for the sliced Wasserstein distance with different number of projections. We observe significant improvements for the proposed approach, particularly in high dimensions. We also use the max sliced Wasserstein GAN for image generation. We train a standard convolutional GAN on the SLAB AHQ dataset with images at the resolution of 512. We're able to train a network without progressive growing or smart architectures. Quantitatively, we also obtain benefits. For this, we look at unsupervised language translation. We show precision at 1 on 5 pairs of languages using the Muse bilingual dictionaries. We're excited to tell you more about our paper at poster number 3. Thank you for stopping by.
All right, questions?
I have a question for the first speaker about the compression story. So back in the 90s, late 90s, there was a lot of this kind of methods being used kind of from the texture literature. For example, the method of Popat and Picard in 97, where they basically did very similar things, but using non-deep, like basically k-means types clustering. What's your opinion? Is it that those methods are just returning back, or is the deep representation really the secret sauce that makes them work better now?
I don't know the works you refer to, but I would say that the benefit here is that you learn statistics of a specific data set, and you can adapt to domains, and I would assume that you would get better performance doing this.
Oh no, they had all of that. They just basically did it with k-means.
Well, I don't know. I would have to compare. I mean, yeah, don't know.
Other questions? All right, I have a question for the third author. Have you looked at other applications where generative adversarial networks are used, not necessarily to generate content, but maybe in domain adaptation? Does it make a difference for other applications, or is it mostly for generation?
Oh, okay. Yeah, I think it's a good question. So we're looking at condition generation, which kind of having the ability for domain transformation. But right now, in this work, the contribution is proposing a new metric for comparing to the distance of two distribution. So I guess it's suitable for all kind of application where you really need to estimate the distance between two distribution. Thank you.
All right, let's thank all our speakers again.
Hello everyone, I'm Kwan-Jun. I'll be presenting meta-learning with differentiable convex optimization. This is a joint work with Subransu, Avinash, and Stefano at Amazon Web Services. In this work, we study the problem of few-shot classification. In this problem, given few-shot training set, we want to compute a classification model that generalizes to unseen test set. Here, shot indicates the number of training samples per category. To begin with, let's see how an example method called prototypical network works during inference. First, we embed the training examples using embedding network F5. Next, by taking the average embedding for every class, we can compute the prototype representation for each class. Finally, given the embedding of test example, classification is done by picking the nearest class prototype. Meta-learning objective is to learn the feature embedding Fi that generalizes well across tasks when used with nearest class prototype classifier. Let's see how we can achieve that. Once you compute the classification model, you can compute the meta loss, denoted here as L meta, which is a measure of generalization error on the holdout test example. Fi is meta-learned by backpropagating the error signal. This is what's happening at the single test level. And you can optimize the generalization error across tasks by learning over a collection of tasks. In our work, we propose to use discriminatively trained linear predictors such as SVM, logistic regression, or ridge regression for computing the classification model. To this end, we have incorporated convex optimizer within the deep network to solve SVM objective. We name our method MetaOpNet. So why is SVM solver better than nearest neighbor-based methods? First, it is adaptive. It is able to do task-dependent adaptation at inference time using both positive and negative samples. Second is scalable. Gradient-based meta-learning methods such as MAML is prone to overfitting as the embedding network gets larger. Also, it is known that SVM can often outperform nearest neighbor in a high-dimensional space. Thus, incorporating SVM solver allows us to use large embedding network. From the network diagram, we observed that to train the embedding network, we need to backpropagate the error signal through the SVM solver. Due to the convex nature of the problem, we observed that we are able to obtain the necessary gradient without differentiating through the on-roll optimization procedure. Let theta star denote the solution of SVM objective. Then the equation in this red box says once we compute the theta star, we can obtain a closed form solution, closed form expression for the gradient of theta star with respect to the input data. However, it involves inverting the Hessian matrix in the dotted box, which is of size dk times dk, which can be prohibitive when the embedding dimension is large. To address this issue, we propose to solve the dual formulation. Since we are able to express the classification model as a linear combination of embeddings of training examples, resulting optimization variable is of size k times n, and n is small for the case of few-shot learning. On mini-ImageNet and tiered ImageNet data sets, when the embedding dimension is low, in terms of test accuracy, we don't see much difference between different learning algorithms. However, when the embedding dimension is high, MetaOpNet improves the result of prototypical network baseline by around 3% with 30 to 50% increase in inference time. We also implement ridge regression-based learning within our framework denoted as MetaOpNet RR, and we observe that it shows comparable test accuracy with less computational overhead. On CVPR-FS dataset, we don't see much difference between different learning algorithms. However, on more difficult FC100 dataset, where class semantic gap between meta-training and meta-test sets are large, MetaOpNet improves the result of prototypical network baseline by 3%. We observed that the performance of our model on both one-shot and five-shot regimes generally increases with increasing meta-training shot. This makes the approach more practical because we can meta-train the embedding once with a high shot for all meta-testing shots. For more details, please visit our poster.
Hi, I'm Adi, and I'm here to present our work on improved training of convolutional filters. We are all aware that CNNs have been widely successful, but this success has come at a cost of overparameterization and added complexity, which means slower inference, and it needs a lot of data to train. And because of this, there has been a lot of surgeons in network pruning and model compression-related works. And when you look at the results of pruning, what this shows us that it is easier to take a larger network and prune it to be a smaller size than to train the same size network from scratch. Here you can see the black triangle versus trained from scratch. So we looked into the filter importance of these COMNETs, and we found that a lot of these filters, they hardly contributed towards the performance of this network. Now, this kind of graph, it is expected for networks like VGG, which has millions of parameters, but we were surprised that similar kind of graph occurs even for a shallow, tiny CONFNETs. Therefore, the question we wanted to ask is that, are these two problems related? That is, inability to train a small network from scratch, and the fact that even in a small network, a lot of the filters hardly contribute towards the performance of the task, even though they are already underfitting. And this is motivated from a lot of results from pruning, which shows most models can be pruned, and from the recent hypothesis which says that it is easier to train deeper networks because it has ensemble of a lot of subnetworks, and you just need one good subnetwork to do the task. Therefore, our first key insight was to train a network such that its filter importance is more uniform, and while training, we will prune and reinitialize the filters in order to explore large number of subnetworks. So when you look at the Reaper training process, it looks like this. First, we initialize a network and train for a certain number of iterations, and then we measure the filter importance. That is, with some criteria. I'll talk about it later. And then we prune the network, and for some iterations, we train only this subnetwork, and then we reinitialize the prune networks. And here you can see at point A, some percent of the filters were pruned, and at point B, these filters were reintroduced, and with a new set of weights, not the same old weights. And you can see this has a lower training accuracy compared to the standard training, which is in the orange line. But however, we are more interested in the generalization, that is the test accuracy. And when you see the test accuracy, when these prune filters are reintroduced, that is at point D, you find that they find new features which are more useful, and they have a better generalization. And you can repeat this process with diminishing marginal returns for several times. And so at this point, the problem is how should we rank these filters in order to do this process? And when we looked at the filters, we found there was a lot of correlation between the filters of the same layer in the CONVNet. And here you can see the layer 2 has a lot of correlation. So our second key insight is to minimize these filter correlations. That is, we find the orthogonal projection of all the filters in a given layer, and then we sum the rows, of course without the diagonal, and then that gives us how much each filter in that layer overlaps with other filters. And we find that this ranking has a very good correlation with the Oracle ranking if you had access to such. And it performs as well as the Oracle, even without needing the lot of computation that Oracle would need. Therefore, the final solution we propose is to train it with a Reaper training scheme, and then to use the interfilter orthogonality ranking. And here you can see on the right, the correlations of the filters when done with this kind of training significantly reduces, especially in the later layers. And here we saw the difference in the result of Reaper and the standard over various other ranking schemes. And we can see that the combination of Reaper and Ortho leads to the best results. And we have more results in our poster if you're interested. And while this technique might be similar to dropout, this process works regardless of whether or not your network has a dropout, which doesn't generally work so well for CONVNets. And our technique compares favorably with dense sparse dense and BAN, which are similar techniques. Although this was designed for shallow CONVNets, we found that it leads to small improvements even in a deeper nets like ResNet 100 and ResNet 152. So in summary, we want to minimize the inefficiencies of filters by reducing the correlation, and we want to allow the model to explore large number of networks by doing this Reaper training scheme. So please come to our poster number 7 and we can talk more. Thank you.
Hi, everybody. I'm Jin Feng from Peking University on behalf of my colleagues to present our work, Tangent Normal or Virtual Regularization for Semi-Supervised Learning. First, recap the setup of SSL. That is, we aim to learn a model with a large amount of unlabeled data and a small portion of labeled data. One important approach is called manifold regularization. That is, we can find a low-dimensional data manifold by the unlabeled data and then learn the classifier with this prior. To make things clear, we summarize 3 important assumptions. The first is that the data is distributed around a low-dimensional manifold, but the observed data contains some noise driven away from the manifold. Finally, for SSL, we assume that the true classifier vars smoothly along the manifold. Therefore, a desired classifier should be smooth along the manifold and robust to the off-manifold noise. Hence, we introduce tangent normal adversarial regularization for this purpose. And this figure shows our proposed model. Basically, we will use adversarial training strategies to separately regularize the smoothness of the classifier along the manifold and perpendicular to the manifold. To go further, let us first revisit several notations. Most of them follows common adopted conventions. We only emphasize the tangent space TXM, which is defined by the column space of the Jacobian of generator G. With these notations, the proposed loss is shown in equation 1. Basically, there are two regularization terms added to the Valina supervised loss, namely TAR and NAR. They are essentially the virtual adversarial losses along the tangent space and normal space, respectively. Thus, to realize our model, we need to first identify the data manifold and then separately perform virtual adversarial training along the tangent space and along the normal space. For learning the manifold, we use generative models with an extra encoder, since we need to know the manifold representation of our data. So actually, there are quite a few models satisfying these requirements. For example, in our paper, we use variational autoencoder and localized again. And now we turn to elaborate the TAR and NAR parts. Thanks to the good property of virtual adversarial losses, it can actually be approximated by the square term in its Taylor expansion. Thus, TAR and NAR becomes equation 5 and 6. Consider TAR, know that the tangent space is actually the image of the Jacobian of the generator G. Thus, we can reformulate TAR, the equation 7, as equation 8. And we further eliminate R by 8, we obtain equation 9. It turns out that equation 9 is actually a generalized eigenvalue problem. Thus, it could be solved by power method and the conjugate gradient, and shown in iteration 10. Surprisingly, by some gradient computation tricks, iteration 10 could be performed by only a few times of backpropagating. This concludes the TAR parts. And for normal adversarial regularization, the main techniques are similar. We transform NAR as equation 12, and it's again an eigenvalue problem, and we can solve it by power method in several times of backpropagating. And finally, we add an additional entropy regularization term to our final proposed loss. And the equation 14 is our final proposed model. And there are several experiments. The first is a two-ring classification problem. We have 6 labeled data in blue color and tons of unlabeled data in gray color. And the curve denotes the learned decision boundaries. We can see that TNAR actually learns the exact true classifier. And the following are experiments on standard SSL benchmarks. We test our method on both SVHN and CVPR, with or without data augmentation. We can see that in all circumstances, the proposed approach, tangent normal adversarial regularization, achieves state-of-the-art performance. So for more details, we'll come to our poster afterwards. The ID is 6. Thanks.
Okay, so we have time for questions, so if all the speakers can come up. And again, we have mics here, I think on the other side. Questions? And I can't completely see everyone at the mic, so feel free to shout if you're at a mic. Okay, so I have one question for the meta-learning talk, the first talk. Have you looked at generalization outside of the task distribution? Do you learn representations embeddings that you can transfer to other tasks, like outside the task distribution. And yeah, you can.
I'm not sure if I correctly get your question, but the one benefit of using SVM instead of nearest neighbor is that when the task difference is large, like a SVM can somehow is able to adapt to noisy embedding.
Yeah, so I mean, you have a mini ImageNet as one of the task distributions, but what about learning on that and then transferring to something else, places?
Probably that wouldn't generalize very well because even with the meta-learning approaches, it meta overfits to some degree, so it's not a magical solution.
Okay, any other questions? Okay, maybe one for the second talk. Did you look at the schedule of when you should drop out the weights and how that affects performance? The schedule for when you drop filter weights?
Yes, so the schedule will matter depending on the size and the number of parameters of the network. So we experimented with mostly vanilla convnets, and in our paper we have a distribution of how often and how many times you should do it. But for the deeper networks, it's very tricky to find the optimal number. But hopefully the ballpark numbers which works for vanilla convnet should transfer to other deeper networks. Yeah. So on a range of 20 to 10 is a good number.
Iterations?
Epochs.
Epochs, okay. Okay, well, let's thank the speakers again, and then we'll move on to the next session.
Hello. The topic I will introduce today is auto-encoding scene graphs for image captioning. And here is a motivation of our method, that we want to use our language inductive bias to transfer some sample visual patterns to more descriptive captions. And when we human observe some sample visual patterns, we may not directly use rigid language to describe them, but we may use our language inductive bias to transform these simple visual patterns to more descriptive descriptions. And here, I show one example that for given one image, we may observe some visual pattern as a person on bike. And with suitable word replacement, we know that this is also person ride bike. And here, the word replacement is one kind of language inductive bias. And the person ride bike is more descriptive and human-like. And here is another example that after observing a yellow banana with some common sense reasoning, we know that yellow banana is also one kind of ripe banana. And here, the ripe banana is more human-like. And here is another example. We may observe that many cars and buses in the street. We human can summarize this phrase as busy street. And here, the busy street is more human-like and descriptive. And for achieving the motivation of this research that exploiting language inductive bias to generate more descriptive captions, we propose auto-encoding scene graphs for image captioning. Here, in this model, we transfer the inductive bias from language domain to visual language domain, and specifically, we preserve this language inductive bias in a dictionary and use this dictionary to generate more descriptive captions. Given a dictionary and some visual patterns, we first preserve this language knowledge into the dictionary. And after that, given some visual patterns as queries, we use these visual patterns to seek the knowledge from the learned dictionary to generate more descriptive captions. And here is a detailed process of our method that we use scene graphs as a bridge to transfer the language inductive bias. Given a sentence S, we use the spicy to pass it into a thin graph G. And after that, we use graph convolution network to embed this thin graph into embeddings and preserve these embeddings into the dictionary D. And this dictionary D is learned by reconstructing the sentence S. And after learning the dictionary D, we remove all the other parts except this dictionary D. And given an image I, we first generate its image scene graph, and then we use this image scene graph as a query to find the corresponding language knowledge from the dictionary D, and use the search language knowledge to generate the final caption, which is S. And for validating our method, we first compare it with a series of baselines. And from the experiment results, we can find that compared with the baseline method, when the graph convolution network is used, the performance can be improved. And when the dictionary is added, we can find that the performance can be further improved in terms of the SID score. And also, we compare our method with some state-of-the-arts. And from this table, we can find that compared with some previous strong baselines, our method can achieve the highest SID scores. And we also show some qualitative examples here. And for one image, we generate its scene graph and the caption. By comparing them, we can find that some descriptions change. For example, the car on road becomes a highway filled with more traffic, and which is more human-like and descriptive. And here is another example. By comparing the scene graph and caption, we can find that the green tree becomes a lush green forest, which is more human-like. And thank you. And welcome to our post position.
Hi, I'm Aditya. Today I'll talk to you about our work on fast, diverse, and accurate image captioning guided by part of speech. This is joint work with my colleagues Jyoti and Live and my advisors Alex and David from the University of Illinois at Urbana-Champaign. Our work deals with the problem of image captioning. In image captioning, an input image is passed through a network. The network generates a caption word by word. A caption is a sentence that describes the content of the image. In this example here, the caption talks about the different food items on the plate as seen in the image. For the same image, 5 different annotators wrote 5 different captions. This shows that many captions are plausible, because obviously there is more than one way to describe any image. However, the focus of most captioning methods is only on generating a single correct caption. In our work, we seek to generate many captions that are correct. Beam search is the textbook method to sample a diverse set of captions from any captioning network. To generate many captions, beam search samples different words at different word positions. However, when using beam search, it is often observed that the same word or the same n-grams are sampled often at the same word position. This leads to high overlap between the generated set of captions and only a few local changes in the final set of captions. In the illustrated example, the 3-gram a plate of food highlighted in red is repeated in many captions. Human-generated captions are drastically different. They don't have such trivial overlaps. We seek to generate better diversity than these trivial local changes obtained by a beam search-like method. GANs and VAEs provide us with a mechanism to generate diverse captions. GANs and VAEs use this framework of an abstract switch. As shown in the figure, the abstract switch, Z1, Z2, or Z3, is fed to the network along with the image. The network uses this switch and generates a caption corresponding to the switch. This switch is often sampled from a Gaussian, uniform, or a learned mixture distribution. This switch has no explicit semantics. In our work, we use this idea of a switch, but our switch will have an explicit semantic meaning. Our switch is an embedding of a part-of-speech tag sequence. First, we generate few part-of-speech tag sequences that are compatible with the image. Then we use these part-of-speech tag sequences to generate corresponding captions. Now our captions adhere to their corresponding part-of-speech tags, and part-of-speech tags are meaningful sentence structures. Therefore, our captions have different meaningful sentence structures. This allows us to generate a good, diverse set of captions. Now we look at some experimental results where we'll compare our method to a few captioning baselines. We'll start by looking at captioning overlap because that's how we motivated our method. mBlue4 measures the 4-gram overlap between different captions. Lower mBlue4 is better. Our POS method, or part-of-speech method, has the least mBlue4 of 0.63. It approaches the human benchmark of 0.51. Next, we look at other diversity metrics. Here, higher scores are better. We find that our POS method generates more diverse 1 grams and 2 grams per caption. It also generates higher percentage of novel sentences, which are not seen during training. Beyond diversity, we look at the accuracy of POS method under BCMR metrics and with a user study. In captioning literature, it's often observed that diverse methods like VAEs lose accuracy. Our POS method is diverse as well as reasonably accurate. It performs better than VAE on BCMR metrics. On a user study, our POS method outperforms both beam search and VAE. These scores and the user study assesses the best ranked caption. Our task is diverse captioning, so we measure the accuracy of top K captions. The x-axis denotes the caption rank K. The y-axis refers to Cider and Spice scores. POS methods, shown in blue, perform better than its diverse counterpart, VAE, shown in red. Note, the beam search methods, shown in green, perform better than our method, but as we saw earlier, beam search lacks diversity. Beam search methods are also very slow. They need repeated inference per word position. Our POS method only needs 1 inference per word position per switch. Depending on the number of captions sampled, our POS method is 5 to 10 times faster than the corresponding beam search. In conclusion, we presented a part-of-speech captioning method. Our method is fast, diverse, and accurate. Do visit our poster number 8 for more details. Thank you.
Hello everyone, I'm Hiroshi Fukui from Chubu University and the NEC Biometrics Laboratory. I talk about attention branch network learning of attention mechanism for visual explanation. Interpreting deep learning is an important research topic. In order to explain the decision making of deep learning, visual explanations such as cluster activation mapping and GradCam have been widely used. An attention map highlights the most informative region relevant to a predict category for visual explanation. We have proposed a new visual explanation model called the attention branch network. Conventional methods for visual explanation enable us to understand the decision-making of deep learning, but they don't contribute to the improved accuracy. For a classification task on the ImageNet, the top one error is increased when we use a CAM. Our proposed method, ABN, improves the accuracy by applying an attention map for visual explanation to the attention mechanism. Our attention branch network consists of 3 parts: a feature extractor and attention branch and a perception branch. The feature extractor extracts feature maps by using convolution layers. The attention branch generates attention map based on the CAM. The perception branch outputs the classification results using the attention mechanism. The network design of our ABN is very simple. First, we prepare the baseline network and divide it into the feature extractor and perception branch. Next, we add the attention branch and the attention mechanism between the feature extractor and perception branch as shown here. The ABN is trained by the 2 losses at the attention branch and the perception branch in an end-to-end learning manner. The attention branch consists of convolution layers module and 2 convolution layers, the same as CAM. The convolution layers module extracts feature while maintaining the resolution of the feature map. After the convolution layers module, we stack 2 K-channel convolution layers, same as the top layer in CAM. To generate an attention map, we apply a 1 by 1 by 1 convolution layer to the first K-channel feature map. The perception branch outputs the final recognition result using the attention mechanism. In order to improve the more accuracy, our attention mechanism has a bypass structure to prevent feature map sparseness. Our attention mechanism emphasizes distinctive area while preventing loss of feature map. This graph shows the accuracy of the latest model, specifically ResNet and DenseNet, wide ResNet, and ResNext on the CFA10 and CFA100 datasets. Here, you can see the top one error of the baseline model indicated by the blue bar, and of our ABN indicated by the green bar. As you can see, the accuracy of recent model with ABN is improved. Let's look at the attention map on ImageNet. In the top and middle example, our attention map highlights almost the same region of GLAD cam and cam. In the bottom example, cam and GLAD cam highlights the different location of the predict category due to misclassification. In contrast, our ABN highlights the right location with the correct answer. Moreover, our ABN can be extended to multiple tasks such as facial attribute recognition. ABN for facial attribute recognition generates the attention map of each task by applying multitask learning to the attention branch and the perception branch. As you can see, the attention map highlights the local facial region corresponding to the predicted facial attribute. Now, I'd like to sum up my presentation. In this work, we propose the attention branch network, which improves the accuracy while obtaining an attention map for visual explanation. The codes for the ABN image classification and facial attribute recognition model are available on GitHub. Thank you for your attention.
All right, questions? You have to come to the other side. There's a microphone on this side, not on this one. Can you yell a bit louder?
Yeah, for the second paper, so how to make sure that the post-tag generated are accurate, how to regularize the post-tag latent space?
So right now we don't completely adhere to the post-tag that's generated, so we have quantized the space of part of speech tags. But roughly, if there are 3 adjectives, they do appear in the caption. So it's a loose embedding of how many attributes, how many objects, how many actions are in the image. That's how we are looking at part of speech tag right now. So there is some lossy caption generation there, but it works to generate diverse captions.
Thank you.
Other questions? Right, then I have a question for the first author, which is, you seem to, I always thought that descriptiveness is a function of the image itself, that you need to look at the image harder to describe it better, but you seem to show that the language model also plays an important role there. And can you maybe comment on this a little bit? So how much do you think you get from language in terms of being more descriptive, and how much you actually have to look at the image harder? Yeah, so if you get more descriptive captions, how much would you need to look at the image to get more information from the image, and how much is it really just adding flowery language to it, or adding better language model to it?
In terms of the CID, the improvement of using better language can be further improved. And from the experiment results, I can observe that compared with graph convolution network, the improvement of the using language inductive bias is it's better.
All right, let's thank all the speakers again.
Today I'm presenting cascaded projections, a method for compressing deep networks I developed with Andreas Savakis. Deep networks are increasingly being deployed on edge devices with computational constraints. Therefore, there's a growing need for methods that reduce the memory and processing consumption of pre-trained deep networks. In this work, we present cascaded projections, a new method for network compression that's end-to-end trainable. Although there are many different approaches to network compression, in this work we focus on weight factorization and pruning methods as they are some of the most popular. Both methods reduce the number of computations in the network by reducing the number of filters. Factorization methods learn a low-dimensional projection of the filters that retain the most information in the features, while pruning methods remove entire filters from each layer of the network and the channels of the filters in the following layers. Both of these methods have their benefits and drawbacks. Factorization methods benefit from the fact that the new set of filters are formed from linear combinations of the original filters. Thus, no information is entirely thrown away. The drawback of factorization methods is that they require the low-dimensional feature maps be reprojected to be processed by the filters of the next layer of the network. Thus, they require additional memory to be allocated for these intermediate feature maps. Pruning methods don't require this reprojection step because they directly remove the pruned channels in the filters of the next layer of the network. The drawback of the pruning methods is that they throw away potentially useful information in these pruned feature maps. In this work, we present cascaded projections, which forms linear combinations of the filters but does not require the feature reprojection. To do this, we learn a joint low-dimensional orthonormal projection which compresses the filters of the current layer as well as the input channels of the filters of the following layer. We impose an orthonormal constraint to improve the tractability of our optimization problem. In order to optimize our cascaded projection, we developed the new proxy matrix method for optimization on the Grassmann manifold. In PMO, our matrix being optimized is unconstrained in the ambient Euclidean space. However, this matrix is not directly used to calculate our loss. Instead, it's a proxy for the closest matrix on the manifold found by retraction using singular value decomposition. In this work, we use this retracted matrix to project the filters and calculate our loss, which is then backpropagated through the singular value decomposition to update our proxy matrix. This optimization method allowed for a loss function which combines intermediate supervision with classification loss, where the intermediate supervision is provided by the reconstruction loss between the compressed and uncompressed network in the figure shown above. This mixture loss generates a compressed network with similar features to the uncompressed network in addition to high classification accuracy. For networks based on the residual network architecture, we don't compress the features between the residual blocks. Instead, we use these intermediate features to calculate the reconstruction loss of the compressed network. A benefit to this design decision is it allowed for simultaneous optimization of all the projections for each layer of the residual network at once. Here we present our results compressing various ResNets trained on the CIFAR-10 dataset. You can see cascaded projections performs quite well for the 18 and 50 layer ResNets for various levels of compression. We also compress the 56 and 110 layer ResNet, and again, you can see cascaded projections performs quite well. One important thing we want to point out is that we present our results with both fine-tuning and without fine-tuning, as we believe the results without fine-tuning provide deeper insight into the actual accuracy of each compression method, and fine-tuning is a very time-intensive process that hides the underperformance of different methods. We next compress the VGG16 network trained on ImageNet to have a quarter of the original number of computations. Again, we first present our results without fine-tuning, and you can notice cascaded projection achieves top performance with only a third of the memory consumption of the top performer. We then show our results with fine-tuning, and here cascaded projection achieves second to the best top performance with only a quarter of the memory of the top performer. In this work, we presented the cascaded projections method for deep network compression. Cascaded projections eliminates the need for feature map reprojection by cascading the compression from one layer to the next. Our method is end-to-end trainable using our new proxy matrix optimization method, and we leverage the flexibility of PMO in order to use a more advanced loss which combines intermediate supervision with classification loss. Finally, our method allows for simultaneous optimization of residual networks at once. Thank you, and I'm happy to answer all questions at our poster, and our code will be available shortly.
Hi everyone, I'm Jaegul from University of Maratua, Sri Lanka, and in this talk I'm going to introduce our work on deep caps, going deeper with capsule neural networks. Capsule networks is fairly a new concept and it promises new direction for deep learning. It also achieves equivariance in the network by introducing dynamic routing between low-level and high-level capsules. Even though capsule networks achieve state-of-the-art performance with less complex data like MNIST, their performance on more complex data is low in comparison to the state-of-the-art convolutional neural networks. So our main goal is to develop a capsule-based neural network with high-level understanding of the images, as well as we want to create a joint representation of the instantiation parameters. Also, we want to create a computationally efficient deep neural network based on capsules. Our network is fairly inspired by the evolution in CNNs over the past decade. From LeNet to AlexNet to ResNet, the CNN's ability to understand more complex features increases when going deeper into the network architecture. So we need to go deeper with capsule networks to fully realize its capacity. So our network is based on concaps layer, which is used to build a modular architecture of a capsule cell. A capsule cell is contain a 4 concaps layer and a bypass skip connection with the element-wise addition. By stacking these 4 of these capsule cells, we will have a deep capsule neural network architecture. We use a 3D convolution kernel to apply a low-level to high-level transformation between capsule tensors. By utilizing the kernel dimension same as the number of atoms in a capsule, we generate a single slice for the high-level capsule tensor. Then by using multiple such kernels, we can produce a final high-level capsule tensors. And by using the strides in the 3D convolution, same as the number of atoms in each capsules, we can apply this transformation separately between each input capsules. Sharing the same kernel across all the input tensors helps to reduce the number of parameters required for the network and make it more memory efficient, and we were able to fit it in a single GPU. Further, a new set of kernels will be used to generate a separate set of new capsules for the high-level tensor, and by applying this dynamic routing on top of these capsule tensors rather than for each capsules, we achieve a computationally efficient concaps layer. The decoder network is used as a regularization to the capsule networks, also as a generator for the instantiation parameters. So the capsule network uses a 0 masked instantiation vector as an input to the decoder, and we use a split vector, only the activated class as an input to the decoder. This allows us to learn the instantiation parameters as a joint distribution across all the classes. Also, this acts as a better regularization term when training the network. Deep caps achieve state-of-the-art performance in the domain of a capsule networks. However, it still lags behind the conventional CNN's performance on classification accuracy. We surpass all the network performance inside the domain of a capsule networks in several benchmarking datasets with a considerable margin. Since the instantiation parameters are learned jointly, for a change in a given instantiation parameter, the decoder will reflect some effect across all the classes. Here we can see a vertical elongation happening across all the classes for a given parameter. By jointly learning the instantiation parameter, we can uniquely identify an instantiation parameter and its effect on the reconstructed images. For example, a change in the 10th instantiation parameter will cause rotation in the reconstructed images. Further, we empirically found that the instrumentation parameter with high variance will cause like global transformations such as rotation and elongation, while the rest of this instrumentation parameter will be causing like more sort of localized changes in the reconstructed images. And thank you everyone for listening, and please visit us at our poster number 11. Thank you.
Hi everyone, my name is Bichun Wu. I'm from UC Berkeley. Today I'm going to present our work, FVNet, hardware-aware efficient covenant design via differentiable neural architecture search. This is a joint work between UC Berkeley and Facebook. So first, why efficient convnets? Today, many mobile and embedded computer vision applications require accurate and efficient convnets. However, designing such network is challenging, and challenges come from 3 ways. The first one is just the intractable design space. Let's assume we're going to redesign VGG16's 13 conv layers, and for each layer we can choose from 3 kernel sizes and 5 channel sizes, and the search space, even so simple, is already intractable. Second is the optimality of the architecture depends on the hardware device, and ideally we should design different convnets for different target devices, but in reality, due to the cost of training and designing neural networks, we can only afford to design one, but deploy it to the other conditions. The third one is, most of our previous work focused on improving the efficiency proxies of the neural network, such as parameter size or flops. However, such proxies do not always reflect the true efficiency that we care about. For example, NASNet A has slightly smaller flops than MobileNet V1, but the actual latency is a little bit slower. Now let's rethink the flow of convenient design to see how we address these challenges. The first one is just manual design that everyone uses. So we start from implicit search space, and we manually come up with the architecture. We train them on the target data set and use the outcome to guide us design future iterations. However, training each neural network takes a long time, and therefore we cannot afford too many iterations, and normally the design is not optimal. Recently, people begin to use neural architecture search to automatically design convnets. So again, we start from explicitly defined search space and use some controller to randomly automatically sample neural architectures and train them on a smaller proxy data set, and use the outcome to refine or train the controller such that the controller will learn how to sample better architectures over time. And this method was successfully discovered models that surpassed the previous manual design, but the problem is they are too computationally expensive because they still need to enumerate and train thousands of neural networks. Our approach is called differentiable neural architecture search, or DNAS. DNAS explore a layer-wise search space as represented by the stochastic supernet. So each layer of the supernet contains several candidate operators, and during the forward pass, we randomly choose the operators according to some distribution controlled by Gumbel softmax. After this is chosen, then we can evaluate the loss on a given data set. The loss not only consider the accuracy, but also the efficiency or cost of the network. The cost is evaluated by deploying each sampled operator on the target device and measure its actual latency. This way, our loss function can consider the actual latency on a given target device. And then we train this loss not only with respect to the operator weights, but also the distribution. And after the training converges, the distribution converges, we just sample from this distribution the final architectures with high accuracy and efficiency. So compared with previous method, instead of training thousands of neural networks, we only train a supernet once, which is significantly faster. The candidate operator of the supernet can be arbitrary, but in our case, we use the inverted residual blocks. Each candidate operator is a variation of the template with a different kernel size, expansion rate, or we can just skip the entire block to save some computation. So using DNAS, we find a family of models called FBNet that surpassed the previous state of the art. So compared with MobileNet V2, we are 1.5x faster latency and 2.4x smaller flops. And compared with MNASNet, they have the same accuracy and efficiency, but the search cost is 400x smaller. This allows us to synthesize different ConvNet for different target devices. So on the iPhone with A11 versus Samsung phone with Snapdragon 835, we synthesized two networks with a similar accuracy. But when we deployed the two models on the iPhone X, the model optimized for iPhone X actually achieved 1.4x speed up. So this is the summary of this work. For more details, please come to our poster. Thank you.
Okay, questions? And I think the mic here works and upstairs. This one might not on the left. On my left. Okay, for the capsules, the performance is getting better and better, but there's still this gap, and I wonder if you can comment on what you think is necessary to get capsules to be at the same level as non-capsule networks.
Yeah, although like the performances keep a little bit increasing, the gap is still there. So I believe the concept of dynamic routing is like kind of like it's good, but it's not that well optimized for the performance on a GPU and so on. So maybe by optimizing the dynamic routing and as well as this instantiation parameter dimensions, like we are now keeping it as 6 or like 8 and so on. So that is not that good enough to capture all the information in a high resolution images. So like ImageNet images. So by increasing like that kind of a research, it will maybe improve the performance, I believe.
And have you tried on ImageNet or high resolution images?
Actually, we haven't tried it on ImageNet, but we try to increase the resolution of the images. Like from CFA images, we increased to 64 by 64, and it's actually gained some improvement in the performance.
Thanks. Okay, questions. We have maybe time for one more.
Question for the last speaker.
Here you go.
So you mentioned having a supernet, but I imagine that's also going to massively increase memory requirements. How do you handle that?
Thanks for the question. So yes, so if we have a supernet, then our memory consumption is larger by, let's say, 8 to 10x, depending on how many branches that we use. But in our case, we are able to train that with 8 GPUs, which is standard configuration. And there are many ways to reduce the memory consumption, like reducing the batch size or training the shorter and so on. And in our experiment, we did not find that. So we found that that does not drastically change the search result.
Okay, great. Let's thank the speakers one more time, and we'll start the next group.
Hello everyone, I'm Ryan Yi. I'm very pleasant to be here to present our work on generating artistic portrait drawings from face photos using hierarchical GANs. This is a joint work with Professor Liu, Professor Lai, and Professor Olsen. We study the art of portrait drawings. Portrait drawings are a long-standing and distinct art form, which usually use a sparse set of continuous graphical elements to capture the distinctive appearance of a person, but it's very time-consuming work. So we want to automatically generate artistic portrait drawings using deep network. GANs have achieved much progress in solving many image synthesis problems. For example, Pixel and CycleGAN are two typical works, but neither of them works well for artistic portrait drawing styles and often generates blurry or messy results. Artistic portrait drawings, also known as AP drawings, are substantially different in style from painting style studied before. First, it's highly abstract. Second, there are stronger semantic constraints for portraits. Third, rendering is not consistent between different facial parts. Fourth, the elements are not located precisely by artists. Last, artists put conceptual lines that are not directly related to low-level features. Therefore, even state-of-the-art image style transfer methods often fail to produce good results on AP joint style transfer. To address this, we propose AP joint GAN, a novel hierarchical GAN structure dedicated to phase structure and AP joint styles. It has 3 highlights: hierarchical structure, novel distance transform loss, and a new AP joint dataset. First, it involves several local nets dedicated to facial feature regions and a global net to capture holistic characteristics to learn different drawing styles for different facial regions. Both generator and discriminator include a global net and 6 local nets. Hierarchical generator transforms input face photos to AP joins, and discriminator distinguishes whether the input join is a real AP join or not. Second, its loss function consists of 4 parts: GAN loss, pixel-wise loss, local transfer loss, and the novel distance transform loss to learn stroke lines in AP joins. Next, we introduce distance transform loss. The elements in AP joints are not located precisely corresponding to image intensities because of naked eye observation and conceptual lines. Using L1 loss alone cannot handle this situation. It penalizes minor misalignments as the same as big ones. So we propose a new DT loss to tolerate small misalignments but penalize big misalignments. DT loss is based on distance. It calculates the sum of distances from the pixels on each line in ground truth to the nearest pixels of the same type in the output image, and vice versa. We use distance transform and chamfer matching to compute it. Third, to train our AP joint GAN, we built a new AP joint dataset containing 140 pairs of face photos and corresponding AP joins for training and testing. We also use a pre-training to compensate the small number of image pairs in our dataset. We use over 6,000 pairs of face photos and NPR results to pre-train our model and use it as an initialization. Next, we show our results. First, we show some results on collected face photos which do not have ground truth artist joins. Ablation study shows that local nets are essential to capture the style of each facial region, and detail loss is essential to produce clean results with delicate lines. Initialization helps to generate good results in less time. Next, we show comparison with existing methods. Our method captures different drawing techniques in different facial regions and generates high-quality results. We also conducted a user study and found our method ranks best in 71% of cases. In conclusion, we propose AP join GAN, a hierarchical GAN, to transform a face photo into an AP join is dedicated to human face and AP join style and achieve successful AP join style transfer. Thank you for your attention. Our poster is number 13.
Hello, thank you for hanging in here for the last session at CVPR. I'm Eric. I work at the Software Engineering Institute at Carnegie Mellon University. This is some work I did while I was at the Air Force Research Labs on allowing users to manipulate the output of a GAN in sort of an intuitive way. So to introduce our method, let me first discuss what interaction with a plain old unconditional GAN looks like from the perspective of a user. Here, the user simply seeks to obtain realistic-looking imagery from some domain. And the domain I'll be using here is, as a running example, will be headshots of people, but more specifically headshots from the CelebA dataset. So to sample from a GAN, as many of you know, you simply draw a random seed from a fixed distribution and use it as input to the generator. And out comes an image. Now, if this image isn't exactly what the user wants, this unsupervised GAN model doesn't provide too many intuitive ways to manipulate the output further. So the goal of this work is to develop a GAN method that allows users an intuitive means to interact with a GAN generator so they can manipulate the output to their liking. So to this end, we developed a constrained generative adversarial network. Our model utilizes a predefined underlying semantic space, here pictured to the right, used to model the properties of images that users can manipulate. This space can represent a wide variety of semantics, including class membership, attributes, objects depicted in the images, and other things. But for this running example, we'll be using attributes such as hair length, skin tone, and gender to manipulate the images using an attribute classifier as the mapping to the semantic space. So some of these attributes are binarized versions of inherently continuous things, but we can use both. So to interact with our model, a user provides input in the form of this relative constraint. So here, the user is querying the model for an image of a person, more like the positive image outlined in green than the negative one outlined in red. The model interprets this as a constraint on the semantic space underlying the model, which defines a region, here depicted in green, of images more similar to the positive image than the negative one. With this constraint, it's combined with previously given constraints, and their intersection defines a feasible region for which the outputs of the GAN should map to. The generator takes this constraint set and a noise vector and produces an image that's within this feasible region. The result is an image that has properties indicated by the user's feedback with respect to the semantic space. The user can then assess the returned image and provide further constraints if necessary. So I want to show one example of the kind of interaction someone can have with our model. For this, I'll be focusing on specific visual attributes for illustrative purposes, but note that our model can accept any non-conflicting set of constraints. I'll be showing the output of our GAN with respect to 3 different random noise vectors, effectively sampling from 3 different places in the feasible region with respect to facial attributes. So to the right of Z1 here, you'll see images produced by using Z1 as input to the generator. On the bottom here, I'll be showing constraints that are used as input to the generator as well. So I'll be iteratively adding constraints from left to right. So each column of generated images above are produced using the constraints below it and to the left. So given the constraint at the bottom in each of the random noise vectors, our model produces the images on top here. Given 2 more constraints, the following images are produced. Again, the 3rd column of generated images on top here were produced using the respective noise vectors in all 3 constraints. Now, for the first 3 constraints, we chose examples that have a single attribute difference between the positive and negative examples, and that is the presence of pale skin. So as a result, we would expect that the generated images have pale skin. According to the attribute classifier we use as the mapping to the semantic space, indeed, these images do have pale skin. And most of the generated images, I'd say, so it says 90% of our Celeb A experiments 90% of the constraints in our Celeb A experiments satisfied the constraints. And the next 3 constraints that I'm showing here have attribute of brown hair as a difference between positive and negative examples. As a result, the hair of the generated images got slightly lighter, or in the case of Z1, the person in the image seemed to grow brown hair. And in the last 3, the difference between the positive and negative images were the positive ones had the attribute of female. Again, in all 3 of the seeded images changed the appearance of the faces, so the mapping to the semantic space gave them the property of the gender female. So intuitively what you see here and what we saw in our experiments is that the constraints define the characteristics with respect to the attributes in the semantic space, while the Z-vectors sort of defined all the other characteristics of images. So that's all I have time for, but if you come see us at the poster, we'll talk about a lot of different things, the memory network architecture, our particular adversarial training procedure, as well as other qualitative and quantitative experiments. Thank you very much.
Hi everyone, my name is Yichun Shi from Michigan State University. Today I'm going to talk about our work on WarpGAN. So WarpGAN is a tool that takes face photos as inputs and generates characters with diverse styles and different exaggeration extent. So the model needs to do 3 things. First, it needs to generate artistic texture styles. Second, it needs to exaggerate face via geometric deformation. Third, it needs to keep the identity of the input face. So the method is simply composed of 2 main modules, one deformable generator and a discriminator. The generator takes the face photo as input and changes the texture and warped image. The discriminator distinguishes both the style and the identity of the input photo and or character. So as any other image translation GANs, the generator in our work has an encoder and decoder to render the texture of the input photo. An additional branch is added to warp the image, the rendered image. In particular, we have a warp controller, which is simply a two-layer perceptron to predict a set of control points and their displacement. And the differentiable warping module takes the control points and their displacement to compute a dense deformation flow to warp the rendered image. And the texture style is conditioned on the latent code S. During training, a style encoder is trained to reconstruct the images. There were two types of adversarial losses in the discriminator. First, there's a patch loss, which takes the last feature map as input. It only distinguishes between the texture style between photos, real characters, and fake characters. And there's a global adversarial loss, whose input is the compact feature vector. It distinguishes both the style and the identity. Here, the style means both texture style and the geometric style. At the end, we have three loss functions. The two adversarial loss function I have just mentioned, and a reconstruction loss is used to ensure that the important content information is not lost by the network. And it also helps to stabilize the training. The deformable generator can be trained end-to-end, and the parameters in the warp controller is updated simply by the signal from discriminator. We obtain a publicly available dataset called web caricature, which has about 6,000 characters and photos of 252 celebrities to train and evaluate our model. The dataset is split into half for training and testing. Here are the results comparing our warp GAN and other style transfer networks such as Cycle GAN and Immunit on this task. As you can see, that style transfer networks mainly focus on the texture style, but ignoring the geometric difference between the input and output domain. Warp GAN can change both the texture and the shape of the input face. Notice that all the images here are from the test split. Here we compare the result of warp GAN with other character generation methods. So warp GAN is better at keeping the identity of the input face, and it also generates exaggerates the face more based on the characteristic of the input face. Warp GAN also allows the user to control the extent of exaggeration by scaling the displacement. It not only works for the celebrities, it also works well for selfies from the mobile phones. Here are more animation results of the warp GAN. Thank you for your attention. For more details, please come to our poster session. It's number 15. Thank you.
All right, we have time for questions. The microphone is right behind you. You probably have to get up and go there.
To the third presenter, during deformation control, how do you ensure that mode collapse is not happening?
You mean the mode collapse of the geometric shape of the So we didn't cover the detail of our loss function. So actually, the global loss function I've just mentioned is a special identity-sensitive loss function, where we treat each modality and identity pair as a class. So in this way, we can encourage the model to exaggerate and deform the input face to the geometric distribution of the character drawn by the artist. I'm not sure whether you're satisfied with this answer.
Other questions? And I have a question for the first author. So I noticed in your data set the images are very well aligned, the input image and the desired output image. How well could you deal with slight misalignments in the ground truth sketch from the original image?
I think our data set does include corresponding image and drawings, but there are still misalignments because the artist draws the drawing by naked eye observation, and so there may be small misalignments. And beside that, the artists often put conceptual lines, maybe in the hair region and other region to show the existence of the facial features. So there are small misalignments in our data set. So that's why we introduced distance transform loss. Thank you.
All right. One more short question. If not, let's thank the authors again.
Good afternoon. I'm Phil. I'm speaking about explainability methods for graph convolutional neural networks. The problem of explainability for convolutional neural networks is well known. Common methods result in a saliency map over the pixels, as depicted in the top figure. Graph neural networks are an exploding area of research. Consequently, there is need for explainability on graph models. To the best of our knowledge, this is the first work to address this concern. Many explanation methods exist for convolutional neural networks. The basic idea is to propagate classification signal back through the network. Each advantage has advantages and disadvantages. We adapt these methods to graph convolutional neural networks. There's at least a decade of work on graph neural networks, going back to Scarcelli 2009. A good resource on this topic is the geometric deep learning community. For intuition, we note that images are very regular lattice graphs. Graph convolutional neural networks generalize convolutional neural networks to handle arbitrary connectivity. We focus on this architecture: 3 graph convolutional layers followed by a global average pool and a softmax classification layer. Graph data is represented as an n by n adjacency matrix and an n by d node feature matrix. Each node has a d-dimensional vector associated to it. We study 2 data sets, molecules and scene graphs, coming from MoleculeNet and the visual genome, respectively. For molecules, atoms and bonds are represented as nodes and edges. Scene graphs are image graph pairs. Objects in the scenes are nodes. The goal is to identify salient substructure in the graphs. We use 3 metrics to compare each method: contrastivity, sparsity, and fidelity. Contrastivity captures the intuition that salient features should differ between classes. Sparsity captures the intuition that a saliency map that highlights the entire graph is not useful. The third metric is fidelity, which captures the intuition that the occlusion of salient features should degrade performance. For example, for CNNs, if we occlude the cat's face, we expect a worse classification. Analogously, if we occlude the salient parts of a graph, we expect a worse classification. The drop in accuracy is a good thing because it shows the features were relevant. So we compared each method on each data set. Here are the results for the molecules. Salient nodes are highlighted in blue, and we can see sparsity and contrastive excitation backprop, the middle columns, where very few nodes are highlighted, and we can see contrastivity in GradCam, the right middle, by noting that different nodes are highlighted for each class. For scene graphs, objects are nodes. Salient nodes are shown with colored bounding boxes. Red is low, green is high. Similar things can be seen as in the molecule case. We can see that the gradient method is not very contrastive, especially compared to contrastive excitation backprop. and GradCam. Here shown are the metrics to average across the data sets and normalized. GradCam was the most contrastive, second highest fidelity, lowest sparsity. Contrastive excitation backprop is sparsest, second highest contrastivity and low fidelity. And contrastive gradient has high fidelity, but low sparsity and contrastivity. In conclusion, GradCam is generally suitable due to its high contrastivity, an important aspect of explanations. CEB is most sparse, suitable for analyzing large graphs. Contrastive gradient has highest fidelity, but is the least contrastive. No method captures all relevant properties. Choose one based on your application. And in summary, we extended common CNN explainability methods to graph convolutional CNNs. We showed proof of concept on 2 data sets, molecules and scene graphs. We compared methods with quantitative metrics. Again, to the best of our knowledge, this is the first work to study explainability on graph convolution neural networks. Please come to our poster number 16. And last, I'd like to thank my contributors, my co-authors, Sohail, Muhammad, Charles, and Heiko. See you at the poster.
Good afternoon, everyone. My name is Ishan, and I'm presenting the generative adversarial density estimator, a work that was done with Jovan Shi and Anton van den Hengel and Lin Chao Liu at the AIML. So with generative models, we are interested in models that can explain what the data is, and they can provide a measure of density. We generally have 2 classes of these methods, explicit likelihood models and implicit ones. The implicit ones are, the best example is GAN. They have very good sample quality, but they won't provide density estimation as we want. What we ideally are looking for is a method that can provide a straightforward sampling method that has density estimation. They are robust to overfitting, and they can model highly multimodal distribution, and they're computationally efficient. For that, we assume that we are given a set of, and they produce good samples. For that, we assume that we are given a good set of data, X here, and we assume that we define a density distribution here similar to exponential families, and we have a sufficient statistics and a normalizer. Usually the normalizer is the difficult one because it contains an integral to be estimated, which is hard, and we have to do that to make sure that it's a proper density function. If we rewrite this objective, this maximization, we'll see that we have an expectation with respect to the data and the density model that if we introduce an alternative distribution Q, we can rewrite the normalizer as you see in the bottom of the page. Then we have 3 terms actually to compute this maximum likelihood with respect to the density that we define. So for the first term is the density, is the expectation of the sufficient statistic. With respect to the sufficient statistic, we compute the expectation. The second one is the expectation of the sufficient statistic with respect to the alternative distribution Q. That's slightly more difficult than the first one. And the third one is the entropy of the alternative distribution. We want to include the distribution, the alternative that we can estimate and can cover the whole data. So the first one, because we only the only unknown is the parameter, we can use the data that we have. We can take the empirical average over the data and compute the and estimate this average, for which we can compute the unknown W. For the second one, which is slightly harder, we can introduce a deterministic function, and similar to GANs, we sample from a distribution and using the deterministic function sample X. And then we can rewrite the expectation in terms of the expectation given the unknown function and the Jacobian of the transformation. And for the entropy, we can write it in terms of the entropy of the prior and the Jacobian of the transformation when you transform from from Z to X. That transformation basically gives you the local properties of the deterministic function that you're considering, and it ensures that you have a one-to-one relationship that doesn't suffer from mode collapse. Putting everything together, we have an alternating optimization between the parameters of the sufficient statistic that define the distribution itself and the parameters of the alternative distribution. We can use it to generate image samples as you do with GANs, and you can see that the qualities are comparably good. Then you can do density estimation with them, and you can ensure that to a certain extent it doesn't suffer from mode collapse. We have used it with visual dialogue as well. In conclusion, our method bridges the gap between the maximum likelihood methods and the GANs. Thank you.
Hello everyone, I'm Martin, and I'm going to present our work called SODEEP, a sorting deep net to learn ranking loss surrogates. Many machine learning tasks are defined by the metric you choose to evaluate them. For example, if you choose to evaluate a regression problem with the Spearman correlation, it implies that you mainly care about the relative ordering of the scores and not their exact value. It would be nice to be able to use this metric, which define the task as objective function. However, in most cases, they are non-differentiable. In this work, we focus on ranking metrics such as mean average precision, recall, and Spearman correlation. These metrics are non-differentiable because they rely on the computation of the rank, which is a discrete value, and the transition from the continuous score domain to the discrete rank domain makes them non-differentiable. We propose to make this metric differentiable by learning an approximation of the rank function. So let's start with an example of a regression problem we would like to evaluate with the Spearman correlation. We have our input image on the left that grows through the model A that we are training, and its output score in blue would typically be used in a loss with the ground to score in light green. But here, we propose to add an additional step between the score and the loss. So we add a sorter S, which is a pre-trained network trained to approximate the ranking function. Putting the score through this sorter will give us the rank associated with the score. So in this example, you can see that the largest element, 0.4, will get the lowest rank, while the smallest score, 0.01, will get the largest rank. Using this rank value, we can now express ranking metric in a differentiable way. Yet, we can still use backpropagation to first propagate the error through a pre-trained network and then through the trained model and update its weight. So now we have gone through the overall idea, we can get into specific. The main idea revolves around the ability to train a model to approximate the rank function. So we tested two types of architecture, one based on recurrent neural network, more specifically on a bidirectional LSTM, and another one based on convolution. After evaluation, we found out that the recurrent architecture performed better both for approximating the rank and when we use it on real tasks. To train those models, we are only using synthetic data, so we choose a combination of different types of distribution, uniform, normal, and regular sampling of interval, and we did a random combination of those distributions. On the bottom right figure, you can see how the model is trained. So we used an L1 loss between the predicted rank and the ground truth rank, which can be easily computed in a non-differentiable way. Now that we have an approximation of the rank function, it's straightforward to derive a differentiable expression for the metric. So here, I'll show you how we did it for the Spearman correlation. Starting from the expression of the Spearman correlation, so it's 1 minus the square difference between the rank of y and y prime. If now we want to maximize the Spearman correlation, we can rewrite it as a minimization problem as follows. So we want to minimize the square difference between the ground truth rank and the predicted one. And now to make this expression differentiable, we just have to replace the ranking function rk by our sorter f theta b. And we now have a differentiable expression for the Spearman correlation that we can use as a loss. So we did similar rewriting for mean average precision and for recall. So now let's talk about experiment. We tested each of these objective functions with a different task. For mean average precision, we choose to use the Pascal-Vogt object recognition challenge, and we obtain competitive results when we add our SODIP loss to existing approach. For the Spearman correlation, we choose to use the video memorability prediction task. So video memorability captures the ability of a human to remember a video a few minutes after seeing it for the first time. And on this task, when we use our SODIP loss instead of a simple MSC, we obtain state-of-the-art result with an improvement of around 1%. Finally, for our loss inspired by recall, we are working on cross-modal retrieval on the MS-COCO dataset. So using an existing visual semantic embedding model, we replace the traditional triplet loss by our proposed approach, and we notice significant improvement on all metrics. So we showed it's possible to make a metric differentiable by learning an approximation of its non-differentiable part using only synthetic data. And using those methods, we obtain competitive results on real tasks. Finally, in this work, we're only focusing on ranking metric and ranking function, but we believe this idea could be applied to other non-differentiable functions if you can generate plausible data. Come see us at poster 18, and thank you for your attention.
Okay, questions for the last speakers, and please do try to stick around. There's only a couple more minutes, and then we'll be done. So questions, I think one over here.
Yes, this is for the generative adversarial density estimation. I was wondering, did you at all look at generating from the distribution imposed by a certain set of labels and looking if this matches the corpus-wide statistics to see if the generator is actually capturing the corpus-wide rather than just the modes, the overall density of the corpus?
So we didn't consider any labels, so it was completely unlabeled, but I think that's a good experiment to be done. But we looked at the, because when you have the Jacobian, I mean, we have an estimate of the Jacobian anyway, but if it is a full rank, you know that you have at least a one-to-one relationship between what you're estimating and the observations, and it seems to be near full rank.
Thank you.
No.
More questions? Okay, I have one for the explainability talk. So you have a bunch of kind of proxies for what we want in explainability, but it still feels like that's not the final downstream way of evaluating explainability. Do you have any ideas on ultimately how you'd verify that this does explain behavior better to humans or to downstream usage?
It's a good question. We're still looking for principled methods, I think, of evaluating explainability methods. You could ultimately just test it with a set of subject humans to see, which ones they prefer. Thank you.
Okay, thank you. Maybe one more question? Okay. I think everybody's ready to go. So this is the final session of the talks, and let's thank all the speakers, these and everyone else, one more time.